So, in this example problem, we're given that an operator is trying to apply a torque to a bolt at point A using a torque wrench, or box wrench, I apologize. The wrench does not turn when the load is applied to the handle, so there's no motion in the system, so it's static. So we're asked to determine what is the torque or moment applied to the bolt, and the force that's applied to the bolt due to the operator's forces. So our first step in this problem is we're going to draw a free body diagram of A, B, C. So in this case, we have point A, and we know at point B we have an applied load. We know from point A to point B is equal to 300 millimeters. All right, and then from point B to point C, we know it's equal to 700 millimeters. Um, all right. All right. So the second thing we're going to do is we're going to apply any support reactions. So in this case, we have the bolt at point A is preventing the rod from translating. So we're going to say that it would have a reaction force A of X and a reaction force A of Y. All right. And then it says that the wrench does not turn when the load is applied to the handle. So in that case, there has to be some moment as well applied at point A that is preventing this bolt from turning. Okay, so the next step is to apply any of our unknown forces, or sorry, our applied forces. So in this case, we have a 52 Newton load that's applied by the operator here, and then there is a 30 Newton load applied at point C, and we were given that the dimensions, or that the force at point B goes along a 12, 5, 5, 12, 13 triangle, and the 30 Newton force is at an angle of 60 degrees relative to the positive x-axis. All right, so once we have our free body diagram drawn, the second step is we're going to apply our equilibrium equations. All right, so we're going to apply sum of the forces in x is equal to 0, the sum of the forces in y is equal to 0, and the sum of the moments about a point is going to be equal to 0. All right, so, all right. So let's start off with sum of the forces in x is equal to 0. All right, so in this case, we just going to list all the forces that have an x component. So we'll have A of x. We'll have the force at point B. We'll have a force along the x-axis of 52 newtons times minus it's going to go along, the force at point B is going to go along the negative x-axis, or its x component is going to go along the negative x-axis, and it's going to be equal to 52 newtons times 5 over 13. Okay, and then we also have a 60 newton force, or sorry, the force at point C is going to be going along the positive x-axis for its x component, and it's going to be equal to 30 newtons times the cosine of 60 degrees. Okay, so if we add that all together, what we end up getting is we get A of x is equal to 20 newtons minus cosine 60 degrees is a half, minus 15 newtons. So you're going to get 5 newtons along the x-axis for A of x. All right. Next step is we're going to sum all of our forces in the y direction and set them equal to 0. So if we do that, we'll have A of y, we'll have minus 12 over 13 times the magnitude at the force at point B, which is 52 newtons, and then we'll have minus 30 newtons times the sine of 60 degrees, which would be the force that's applied at point C. So we would get A of y would be equal to 12 over 13 times 52 newtons plus 30 newtons times radical 3 over 2. If we add all those together, what we end up getting is 73.981 newtons, which is about 74.0 newtons. All right, and then our last step is to sum our moments about point A and set that equal to 0. So at point A, we have a couple moment, M of A, and then we have, so we're only going to include the y components of our forces times these moment arms, because the forces along the force components along the x-axis of force B and force C will not create a moment about point A, so we're only going to care about the moments caused by the vertical components of these forces. So the force at point B has a moment will have a magnitude of 12 over 13 times 52 newtons. All right, and then that's going to be going to create a clockwise moment, so that's why it's negative. All right, and then the same thing for point C is going to be equal to 30 newtons. Sorry, and then the last thing I forgot to multiply by is the moment arm, which is equal to 300 millimeters. Okay, and then for force B, it's going to be equal to 30 newtons times the cosine of 60 degrees. It will again create a clockwise motion, and then the moment arm for this force is 700 millimeters from point B, or point A. All right, so if we add these all together, M of A is going to be equal to 48 newtons times 0.3 meters plus 25.981 newtons times 0.7 meters. All right, if we add these all together, what we end up getting is we get 32.5867 newton meters. All right, which is about 32.6 newton meters for the moment about point A. All right. So that concludes this problem. So just to recap again, we drew our free body diagram based off of the information that was given to us in the original problem statement, and the diagram on the problem. Once we had our free body diagram, we used it to apply our three equilibrium equations. In this case, all of our summation equation, for each time we summed up the force in the x, the force in the y, and the moment about a point, we only had a single unknown, so we were able to just directly solve for each of the three unknowns, a of x, a of y, and m of a.